Okay, let's start. A very good afternoon, everyone. Welcome to this problem solving session. It's week 8, and today we'll also be seeing control system design part, and we'll be designing lag and lead compensators using root locus technique. So before we begin our lecture, just for the sake of recapitulation, let's try to solve this question of root locus so that we are on track and then we are able to design these lag and lead compensators using root locus. So question is, a unity feedback control system has an open loop transfer function g of s is equal to k divided by s into s plus 4. Draw the root locus and determine the value of k determine the value of k if the damping ratio zeta is 0.707. So I'll be beginning with this question so that the rest of the analysis becomes easier and your root locus concept is also revised. So we are given an open loop transfer function g of s as k divided by s into s plus 4. We have covered this root locus stuff in detail, so I would assume that you all are aware how we draw the root locus, right? So basically, root locus is the locus of like we see the open loop transfer function, and then by varying this gain k, we get like how this locus, how the locus which we obtained is actually the locus of closed loop poles. So by studying open loop transfer function, we get the characteristics of closed loop transfer function, closed loop poles. So how should we proceed? So we have two poles here. One is at origin, s equal to 0, and other is at -4. So the number of branches of the root locus will be 2. And uh, so let me draw it. So we have one pole at origin and another pole at -4. Right? So yes, we have -4. Then, so how should we proceed? The root locus will be something like this. There will be a breakaway point somewhere here, and the root locus will go somewhere like this. Right? Is it clear? So we have a root locus like this, and the angle of asymptotes is 90° and 270°. So that's all clear. Now let's try to find this intersection. So this is a breakaway point as well as centroid. So this centroid, how is it calculated? Summation of real part of poles minus summation of real part of open loop zeros, that is summation 0 minus 4 minus 0 divided by p minus z. P minus z is 2 here. So it will be minus 2. So this point is minus 2. Okay, so if you calculate the breakaway point, that will also come out to be minus 2. Can anybody tell me how we calculate breakaway point? Yes. We actually take the characteristic equation, then differentiate that characteristic equation with respect to s, put that equal to 0, and get the value of s, which is the breakaway point. Okay. Now we are done with root locus. The other part is we have to find the value of k if the damping ratio is 0.707. Right. So what we are given zeta is 0.707. So we have to find the damping ratio. We have to find the value of gain k. So we know that cos of theta is equal to gamma. So theta will be cos inverse of gamma, zeta. And theta will be 45 degree. What is this theta? This theta is the angle made with origin. Right? So this is 45 degree. Now, how can I find the value of gain k? Right? So now can we find this point, the intersection of this line with the root locus? We know this part is 2 and this is 90 degree. So if we write tan of 45 degree, so what will be tan of 45 degree? Tan of theta. That will be this. Let's assume this is x. It's x by 2, right? And tan of 45 degrees 1, it implies my x is equal to 2. So this point, this is j omega x's. So this length is also 2. So what will this point be? Is minus 2 plus 2j. Right? So this is minus 2 plus 2j. This is the intersection of this line with the root locus. Now, how do we find the value of k from the root locus? One way is, there are actually two ways. One way is you take the product of the distances of all the poles to this point divided by the product of the distances of all the zeros.
Sir, excuse me, sir.
Yes,
This
yes.
is 2x or x, sorry, this distance?
Oh, no, this is actually x is equal to 2. Should not get confused. So how should we find the value of k? For example, we have two poles here. One is at -4 and other one is at 0. So we take these distances and this distance. So k, the value of k is product of distances from all poles to that point, to the point here that is -2 plus 2j, or to point divided by product of distances of from all the zeros to that point. So what is k here? Now, can anybody tell me what is this distance and what is this distance? Because multiplying these two distances will give me the value of k, right? So we know this is minus 2. Sorry, this is 2, this part. And this we calculated also as 2. So we can use, similarly, this is also 2. So we can use Pythagoras theorem and find this length. Assume this is y, or this is y1, whatever. So by using Pythagoras theorem, we can find y1 as 2 square plus 2 square. That's equal to 8, which, sorry, y1 square, which is equal to, it implies y is equal to, what was our 8? 2 root 2 is equal to 2 root 2, right? So this part is equal to 2 root 2. Similarly, this part is also equal to 2 root 2. Then then this distance is 2 root 2 into this distance is 2 root 2. There is no 0, so the distance is 1. So my k will be 2 root 2 into 2 root 2 divided by 1, which is equal to 4 into 2, 8. So it implies my gain k is 8. So this was one method, right? So other method is, we have learned when we were learning root locus that, so since this point lies on the root locus, so it means it should satisfy
So
the
this
magnitude.
minus 2 plus j 2j, this is a dominant pole you have found?
No, right now I'm not talking anything about dominant poles. It's just a simple root locus question,
So
right?
you have
So
find the roots of this
I
for
did
root of.
nothing. As of now, I have just, so this was the question, maybe because you joined late. So this was the question, g of s k divided by s into s plus 4. The question was to draw the root locus and determine the value of k if the damping ratio is 0.707, right? So I did nothing. I just drew the root locus. Then we were given that the damping ratio is 0.707. So what does it mean? It means that cos of theta, the angle which uh, will be made with the origin, will be 45 degree, right? So then I calculated,
How did we
so
get this pole, sir? Minus 2 plus j2.
yeah, that's what I'm saying. So I calculated theta.
Okay.
Okay, so I calculated theta here. Then this theta, it intersects this point, this root locus here. So I
Yes,
don't
yes.
know what is the value of it. Then I found it using basic trigonometry. So I know this length, this is 2. Similarly, this is a right triangle, and this is
Yes, yes, yes.
then
This
from
got sir,
tan
got sir.
40. Yeah.
Yes.
So now second thing is what I was saying. This point is already lying on the root locus. Now, when this point is already lying on the root locus, it means it should satisfy the magnitude condition, right? So it means k divided by s into s plus 4, the magnitude at s equal to, let's assume, uh, I'm labeling it as s1 is equal to 1, where s1 is equal to minus 2 plus 2j. Correct. Since this point is already lying on the root locus, it means this magnitude condition is satisfied. It means we can solve it, means k divided by, if we put the values, it will be minus 2 plus 2j into minus 2 plus 2j plus 4. This should be equal to 1, or by simplifying, we get 2 square plus 2 square into 2 square plus 2 square equal to 1 implies k over root 8 into root 8 is equal to 1, which implies k is equal to 8. Is it clear?
Yes, sir. Yes.
Anybody having any question till here? Because I will be using these things again and again. We'll have to use a lot of trigonometry today. So that's why I wanted to revise using this question so that root locus as well as the basic trigonometry is also revised. Okay, so if nobody has any question, then when I taught you root locus, I told one very important thing. That was the effect of adding poles and zeros to root locus, like to the open loop transfer function. What happens to the root locus if we add poles and zeros to it? So can anybody tell me what will happen if I add poles to an open loop transfer function?
Yes, when you add poles, then your system may become unstable.
Yes. So, but what happens to the root locus?
Root locus may pass in the right half of the S-plane.
Yes. So addition, the effect of addition of poles to the open loop transfer function is that the root locus shifts towards the right. So if it shifts towards the right, it means the relative stability is decreased. Similarly, when we add the zeros to an open loop transfer function, the root locus shifts towards the left so that the relative stability is improved. Okay, so I'll just write these two lines. The addition was to the open loop transfer function has the effect of shifting the root locus to the right. And what does it happen? It means it lowers the system's relative stability. Similarly, the effect, like the addition of zeros to the OLTF, has the effect of shifting the root locus to the left. It implies it increases the system's relative stability. Okay, so this is these concepts we'll be using while we design lag and lead compensators. So please remember this, that addition of zeros, it improves relative stability, and addition of poles, it decreases relative stability by shifting the root locus towards left and right respectively. Now let's start this lag compensator design. This lag, see, we have two characteristics. We have transient characteristics, we have steady state characteristics. This lag compensator is basically used to improve the steady state characteristics. So it's used to improve the steady state response. When we studied about controllers, which controller was used to improve the steady state response?
Derivative controller,
No,
integral.
steady state. Yeah, integral. A better PI because yeah, or integral we can say. So here also, like if we want to improve the steady state response, and what is the steady state? What does this mean to improve the steady state response? It means our steady state error should be as low as possible. So if we want to minimize our steady state error, then we design this lag compensator, right? So, and it's always connected in forward path, like when we studied the controller, we said the controllers are always connected in forward path. Similarly, these compensators as well, they are connected in forward path. Like for example, if we have a system G of S like this, where some gain with some gain K, so if we have this system, then and let's assume this is a type 0 system. So if it's a type 0 system, there are no poles at the origin, then this open loop transfer function, KGS, we can write as KGS is equal to uh, K as it is. And let's assume there are M zeros divided by S plus P1, S plus P2, so on up to S plus PM. Right, so I considered a type 0 system, right? So when it's a type 0 system, what will be the steady state error, right? So for a unit step input, the steady state error will be E infinity is equal to 1 divided by 1 plus KP, right? So what is this value of KP here? KP means limit S tends to 0, K into G of S, which is equal to, if you put S equal to 0, it will be K into Z1, Z2, so on up to Zm divided by P1, P2, so on up to Pm, right? So this is the steady state error. And the task of this Lee compensator is to increase this Kp, so that when this Kp is increased, our steady state error will be decreased, right? So so as of now, there is no compensator added to the system. I just uh, uh, took this system without any compensator. Now let's add a lag compensator with this, right? So it will be something like this. We have K, then let's assume GC, which is the transfer function of a lag compensator, and G, this, right? And the transfer function of lag compensator, it's given by this Kc S plus Zc divided by S plus Pc, right? So it's in general, this is for both compensators. The difference I'll tell you later, where is the difference, but as of now, just remember, so this is the transfer function of a compensator, be it lag or lead. The differences will come soon. So now, so these are in cascade. So what will be Kpn? Let's assume now the Kp, which is new, and let's assume this was Kp old without compensation. Now this Kpn will be limiting S tends to 0, K into GC of S into G of S, which will be equal to K Z1, Z2, so on up to Zm divided by P1, P2, so on up to Pm into Kc, Zc, Pc. I just did nothing. I just put S equal to 0. So this is as it is. This is KPO, which was earlier there. So this is KP old, and this term is new. So if you see here, the goal is to increase this KPN. The goal is to increase this KPN. Why? Because if KPN is increased or this KP is increased, then our steady state error will decrease. And we know that we design this lag compensators to improve the steady state response. So the goal is to increase this KPN. So how should we increase this KPN? By increasing this ratio, ZC over PC. So if this ratio, if ZC over PC is large, it implies KPN is large, which implies E steady is, or we simplify E steady state error, it decreases. Right. So basically we have to make sure in case of a lag compensator, we have to design such a way so that this ratio is large. ZC over PC is large. Right. So because when this is large, then this KPN will increase. When it increases, the steady state error will decrease. But if you see here, this is a 0, ZC, and PC is a pole. So if we are adding this 0 and pole in the transfer function, in the system, we are somehow also contributing to the transient characteristics, right? Because right now, like I just told you that adding a 0 shifts the root locus to the left, and adding a pole shifts the root locus to the right. So I'm actually adding a 0 as well as a pole. So it will actually response. It will actually disturb the root locus. But here we do not want that happen. Right? We only want steady state characteristics. Our desire is to obtain to improve the steady state response without impacting the transient characteristics. But we are adding a 0 as well as a pole, so transient characteristics will get impacted. So how we can avoid that, right? So how we can avoid that? So effect on transient characteristics. So we have this GC of S, that is the lag compensator transfer function. It's KC S plus ZC divided by S plus PC. Correct. So now if we want that transient characteristics are not impacted, then we should place these poles and zeros close to each other, right? Because poles give a positive angle. So if we add zeros and poles to a transfer function, so zeros give a positive angle contribution. Similarly, poles give negative angle contribution. If we like place these poles close to each other, then their effect will be cancelled, right? So if their effect will be cancelled, then our transient characteristics will be the same. Our root locus, it will not impact our root locus. So the trick is place these poles and zeros, pole and zero, they should be placed close to each other. But I told you this condition also, like we have to ensure that this ZC or PC, this ratio is large. So how can we ensure? How can we ensure that ZC and PC, the ratio is large, as well as the poles and zeros, they are placed close to each other? Is it possible to attain? Anyone? So we have to ensure two conditions. One is we have to place these poles and zeros close to each other so that their effect does not contribute to the transient response. At the
Pole
same
should
time,
be
we have,
close to the origin.
okay, okay. So two things are there. One is this pole and zero, they should be close to origin. They should be close to each other. And other one is PC, ZC or PC, it should be large. So why they should be large? Because we want to improve the steady state response. And why these poles and zeros, they should be close? Because we don't want, I'm writing here, transient, so that transient is not impacted to achieve better to improve steady state response. Now let's see some combinations. If PC is 0.01 and ZC is 0.1, so are they close to each other?
Yes.
Yes. So they are close to each other, and the ratio is ZC over PC is 10. They are close to each other as well as the ratio is large. Similarly, if you take this combination, PC is 1 and ZC is 10. The ratio is 10. The ratio is 10 again, but we cannot choose this combination. Why? Because this will impact the transient response. It will distort the transient response, right? But
They
both
are
these,
not close to each other.
yes, but both these combinations will improve the steady state response,
Yes.
right? So as soon as we finish this class, what I would recommend every one of you, that whatever we do in today's class, try to simulate this in MATLAB so that you'll get a good feeling. Because here, if you take this combination of ZC and PC and use this in cascade, use this in feedback, then you will see what happens to the transient response as well as the steady state error. You will see by using this combination, the steady state response will be same, but the transient will be impacted. So you'll get a good feel of it if you do this in MATLAB as well. So the main thing is, while designing a lag compensator, you have to ensure your ratio of ZC or PC is large. At the same time, in order for the transient response to be not impacted, they should be placed close to each other so that the effect of poles and zeros is cancelled. Right? So now let's do a question.
Sir, can you consider the zero as a value of pole which is given in the example?
Sorry, I didn't get you.
Suppose we have to add the zero in the system for the
Mm-hmm,
compensation and
mm-hmm,
pole. So
mm-hmm.
can you consider the value of zero,
Same,
the same value
same.
of the pole which is
Yes,
given in the example, to
yes. You
cancel the
see, yeah, exactly. It depends on the design. It depends on what you are looking for. So sometimes, for example, you have a third order. While you design a compensator, you get a third order system. But whatever these specifications we have, like overshoot, settling time, they are all designed for second order systems. So in that case, if you design a compensator in such a way so that your poles and zeros are cancelled, then the resulting characteristics you'll get, they will be more accurate. But if you place them close to each other or far away from each other or like not that close to each other, then maybe you do not get a second order system, but the calculations or the formula you have, like for the overshoot, settling time, they're all only designed for second order system. So in that case, your calculations or they will not be that accurate. You'll be close to what what you want to achieve, but yeah, they will be not accurate. So this all will come if you practice this in MATLAB. But yeah, we can do that. We can place poles and zeros exactly like the same, and we'll see that in later examples. Now the question is, we have a transfer function g of s given by 164 s plus 1 s plus 2 s plus 10. Design the lag compensator to improve the steady state error by a factor of 10. Can you try? Can anybody try?
Sir, I have a doubt, sir.
Yes, please.
Sir, can we do a problem with the value of the roots as complex number, sir?
Mhm.
Any problems with the roots of the root value as complex number? Because we are taking s is equal to -1, -2. So they are real roots with the
Okay.
complex number values for the roots. The design will be the same or will it go different, sir?
See, if you are talking with respect to your assignments, then are you talking with respect to your assignments?
No, no. I'm in general
In
how to
general.
proceed with complex numbers. I'm asking, sir. Not
So we have,
relevant assignment.
yeah, we have plotted root locus for complex poles as well. They're a bit
Okay.
complicated, but there you have to see angle of departure, angle of arrival. But yeah, the design criteria, it remains the same. It will be complicated or involved a bit, but yeah, I think in your assignments or in this course, you won't be getting those type of questions. But yeah, more or less the design remains the same.
Mm-hmm.
But while we solve some more problems or while design lead compensators, we will use dominant poles, or we will be using we'll have to consider some design specifications for which there will come these complex poles, and in that case maybe things will be more clear.
Okay, sir. Thank you, sir.
So can you try this question? So the question is, you have given a open loop transfer function, and you want to design a lag compensator to improve the steady state error by a factor of 10. So can you first calculate the steady state error for this uh, system, for this open loop system? First
Steady
of all, you
state
should
error
be
is
able. Yes.
steady state error is given by us. It is given, no? 10.
So you have to identify. See, is it
Yes.
what is the type of this system? What is the type of this system?
Type 0.
It's a type 0 system. So when will steady state error be finite for a type 0 system?
KP.
When we have a step input.
Step one.
Yeah, so when we have a step input, then the steady state error for a type 0 system will be finite. And in that case, the position that the steady state error, for example, E infinity, it will be given by 1 divided by 1 plus Kp, right? And what is the value of Kp? For example, I am calculating uncompensated Kp. So I'm assuming there is no compensator that is added to this system, and I need to find the steady state error. So again, I know that it's a type 0 system. So in order for steady state error to be finite, obviously the input has to be a unit step. right? So what will be Kp? Kp will be limiting s tends to 0, g of s, right? So, and this will be 164 divided by 1 into 2 into 10. And this will be 8.23. So my Kp comes out to be 8.23. And what will be my steady state error? It will be 1 divided by 1 plus 8.23, which will come out to be 0.108. Right. So this is the steady state error when there is no compensator added. Now, what we are saying, so the question says you have to design a lag compensator. So we already know by designing a lag compensator, we will improve the steady state error, we'll decrease it. But the question is specifying to decrease it by a factor of 10. Right. So my new error, it should be my, as per the question,
So we have to add the pole and zero, na sir?
you like it depends. Yeah, of course, when we are designing a lag compensator, obviously we have to add a pole and a zero. But yeah, let's go step by step because this is the first question we are solving. So let's go step by step, otherwise we'll get confused. So what is my requirement as per question? That is, my steady state error has to be reduced by a factor of 10. My already steady state error is 0.108 and it has to be reduced by a factor of 10. And what is this steady state error? This is 1 divided by 1 plus Kp, but this is new Kp. This is compensated Kp. And this is equal to 0.108 divided by 10. If you solve it, what is the value that is coming for Kpn? $91.59. Is it coming for everybody? So my Kpn, my new value of K should be 91.59, so that my steady state error is reduced by a factor of 10. Now what I need to design, I need to design a lag compensator, which is the value of which is given as K divided by S plus ZC divided by S plus PC. One more thing you should remember is this: ZC over PC is equal to KPN divided by KPO. That's this old K. Or in other words, I can write it's equal to K desired or K compensated divided by K uncompensated. Right? So in this case, what will be my ZC over PC? My ZC over PC, it will be KPN is 91.59 divided by 8.23, which is equal to 11.13. Oh yes, the difference is large. So that's why we are getting we're getting our steady state error to be decreased by a factor of 10. Now see.
So this KPN is 91.3, na?
Whatever it is, 91 point, how much you are getting? 91.3.
Okay.
That's okay. 91 you are getting, so that's fine. That should be fine. So there won't be much difference. So ZC over PC, is equal to 11.313. So if we now, there are n number of ways to come up like with the design, because we can always fix one. Let this PC is equal to 0.01. Then since ZC over PC is 11.13, it means my
Sir,
ZC will be,
new case
yes.
decreased by 10%. New case decreased by 10%. That means ratio should be
No, I
91.5.
where did I tell that new K is decreased by 10%? In my question,
Actually,
I said the steady state error should be decreased by a factor of 10, not new K. There's a difference between steady state error and K.
yes, yes,
So here I wrote this steady state error, as per the question, it should be decreased by 10. Then I need to find new K, the compensated K. Is it okay?
okay, sir, okay.
Then, so what I was saying, so if you take PC as 0.01, then given that ZC over PC is 11.13, you should get ZC as 0.111. Similarly, if you take PC as 0.001, then ZC will be 0.011, right? The ratio is same. The ratio is same, but yeah, again, I told you there will be uh, difference, different behavior in the transients. So what you do for the same lag compensator, try to use this poles, this combination P and PC equal to 0.01, ZC equal to 0.111, then PC is 0.001, ZC is 0.011, and see the effect in the step response. So that's what I said. As soon as we finish this class, you must like work like these examples in MATLAB. You must go through at least once. You'll get a good feeling, because this design part is like the answers are not unique. Like if I'm giving the same problem to n number of students, n students can come up with n different answers for the same problem, because this design is different. Design, like the answer cannot be unique. There are n number of ways to design for the same number of specifications. So if you have understood this, now let's do one more question. The open loop transfer function is given as g of s k divided by s into s plus 2, right? So this is the open loop transfer function, and it is desired that the compensated system meets the following specifications. So now what happens? We are given this transfer function, then the question is saying that we're designing a compensator, but we do not know which compensator. The question is saying it's desired that, okay, I'm writing this. It's desired that the compensated system meets the following specifications. Right? So my velocity error constant, that's equal to 20. My peak overshoot is equal to 16.3%. My settling time is equal to 4 seconds, 2% tolerance band. Now, the question number 1 is find the dominant poles. Find the dominant poles for the same. So if you have gone through the lectures, like dominant poles are the poles whose contribution on the transient response of this, like who have the dominant contribution on the transient response of the system. And they often occur in complex conjugate pairs. So let me solve this question for you. So we are given this maximum. So peak overshoot is given as 16.3%. So if I use the formula for this peak overshoot, 0.163. So can you solve and tell me the value of zeta? What will be zeta?
Zeta is 0.5.
Great, yeah. Everybody should have calculator because the calculations will be like complex. So if my zeta is 0.5 and also I'm given the settling time is how much? Settling time is 4 seconds. Sorry, how much is settling time? Yeah, 4 seconds. So settling time is given by 4 by zeta omega n, which is equal to 4. 4 and 4 goes. It implies 1 over zeta omega n is equal to 1. Omega n is equal to 1 over zeta. It implies omega n is equal to 2. Is it clear? Anybody is having any doubt here till this?
Sir, dominant pole is -1 plus minus j 1.73.
Yes. Yeah. So let's write dominant poles. Dominant poles are given by this formula. You should remember this: minus zeta omega n plus minus j omega n under root of 1 minus zeta square. Right? So when you put the values, your dominant pole will be -1 plus minus root 3j. Is this the same you were getting?
Yes, sir.
So normally in your assignment, you will be asked about the magnitude because there will be like I think no options. So you'll be asked about the magnitude. So these are the dominant poles, and basically in most of the cases, these dominant poles are the desired poles because they have the dominant effect on the transient response. So if we study the effect of these poles, then more or less we study the response of the whole system because they have the dominant response. So studying them is sufficient. Like we can neglect the other poles.
Sir, sometimes it is also as angle, find the angle deficiency.
Yes. We'll do those questions. As of
Okay.
now, we are just doing lag compensation. So when we do the lead compensators, there this angle deficiency will come. So we'll do them in 5 or 10 minutes. We'll be doing those questions. So the question number 1 was to find the dominant poles. The question number 2 is find the value of gain k. Right? So there is this there is this gain k. So you need to find this value of gain k. Okay, one more thing. So we are given these specifications. Settling time is 4 seconds and this overshoot is 16.3 seconds. It means these poles, these dominant poles, it means like when we put the value of these poles in this transfer function, like when we put S equal to SD or dominant poles, we get this specifications. We get this overshoot as 16.3 as well as the settling time as settling time as 4 seconds. So they are the desired poles, right? So now the question is if only a gain adjustment achieves the transient performance, what is the value of gain k? So I'll tell you later what is gain adjustment. But as of now, just try to find the value of gain k as we did in the first question while we were doing root locus. So can we plot the root locus of this system? So the root locus will be one pole is at 0, other pole is at -2, right? So can you find centroid? Anyone? Yes, anyone can find the centroid. So the root locus will be something.
-1.
Yes, the centroid is -1. So this is -1, this is 0, right? So this is the root locus of this system. Now we have to see, we have to locate this dominant pole, the desired, which is actually our desired pole in this root locus. Are we able to, can we locate it? So see, this is our desired pole. So let's try to locate it in the.
Real part is -1 and imaginary part is √3.
So it will be something here.
Yes, yes.
Similarly, something here because it occurs in pairs. As of now, let's only take one. So this pole will be something here. So it's already lying on the root locus, right? So it means if I put the value of this in my open loop transfer function, then magnitude condition should be satisfied, right?
Yes.
So my magnitude condition is G at this SD, this is equal to 1 and it should be satisfied. It means K divided by S into S plus 2 at S is equal to SD, it should be equal to 1. And what does it mean? It means that K is equal to magnitude of SD into magnitude of SD plus 2, which implies K is equal to, just put any value, it will be 1 square plus √3 square into 1 square plus √3 square, which is equal to 4. So the value of K is equal to 4. So now can we calculate this from the root locus? So we can calculate it from the root.
Second is 1 square plus 1 square. No?
Yes, 1 square plus under root. No, sorry. What is the number? It's -1 plus minus j√3.
SD plus.
Yes. It's 1 square plus √3 square. It's actually -1 square plus √3 square. Similarly, 1 square plus √3 square, because 2 minus 1 is 1. Right. So what I was saying, so can we get the value of gain K from the root locus? So this distance is 1. This distance is √3. We can easily get this distance. This will be 2. Similarly, this distance will be 2. Then my K will be product of distances from all poles to SD divided by product of distances from all zeros to SD. Then that will be, my K will be 2 into 2 divided by 1, which is equal to 4 from the root locus. Is that okay? So here we do not need to, as of now, we do not need to design any compensator, be it lead or lag, because our desired pole is already lying on the root locus. If this desired pole would not be lying on the root locus, then we have to do something. we have to do either lag compensation or lead compensation in order for this desired pole to come on the root locus. Then our performance specifications will be met, which we will see in other questions. Now, let's do another part of this. Again, the velocity error constant, that's given. So Kv is given. Kv is given as 20. Now the question is, so this is desired. So this is when we apply the compensation. So what will be the velocity error constant of the uncompensated system? So uncompensated.
It is given as 20.
No, it's not uncompensated. That if you read the question,
Yes, yes, yes. It is compensated. Okay, sir.
yeah, it's compensated. So what will be for uncompensated? Can you calculate? Its velocity. So I will be limiting s tends to 0, s into g of s. Right? So it will be s into 4 divided by s into s plus 2. S and s will go. 0 and 0 will go. Yeah, this will be kv uncompensated will be equal to 2. Okay, so kv uncompensated will be equal to 2. Now I told you the ratio, like let's assume I'm designing a lag compensator. So if I'm designing a lag compensator, my ZC over PC, that should be equal to my kV compensated divided by my kV uncompensated. So here it's coming out to be 20. It's given 20 and its uncompensated is given 2. So it's given as 10. So my ratio will be, so if I'm designing a lag compensator for this system, my ZC over PC is 10, right? Now, the question is, assume we design a lag compensator, then what is the value of beta? Find beta. So you should be knowing, you have gone through the lectures, you should be knowing the general form. Like we can write lag compensators in many ways. I wrote like this. GC of S is equal to KC S plus ZC divided by S plus ZP, sorry, PC.
Sir,
So I
actually, this
wrote
is
it like
value of beta.
we have to find, yeah, this is value of beta, but we should know how it is coming. So
So,
so
no, no, there is a formula, sir. Beta is equal to kV desired by kV uncompensated. This
that's
same formula.
true, but yeah, it's coming like this. See, for example, I can write this lag compensator also like this. That's GC of S is equal to S divided by 1 plus tau divided by S plus 1 by beta tau. So this is what beta is. In this form, this beta should be, beta is, so this beta they're asking, find this beta. Right? So I know my ZC over PC. What is ZC here? 1 over tau divided by what is PC? 1 over beta tau, which is equal to here 10. This is equal to 10. So this and this will go. It implies my beta is equal to 10. Either you can directly find, that you can write directly beta here, but from this way, you can also find ZC or PC that you know that's given as 10, and ZC or PC from this is the 0, this is the pole. Just put in the values, you'll get beta equal to 10. Is that clear?
Yes, sir.
Now there is another question. The question is, with the 0 of the lag compensator, ZC at minus 0. No, sorry, this is not the question. The question is, with the pole of the compensator PC at minus 0.01, the compensator pole 0 is located as. The compensator 0 is located at. So you're given PC as 0.01 and you have to find the compensator pole. Again, you know, ZC over PC is equal to 10. ZC over PC is given as minus 0.01. It's equal to 10. It means what is ZC? 0 minus 0.1. Is it clear? ZC is minus 0.1. So these type of questions you will be asked.
So this is a sub question, sir, in given example.
Yeah. It's a sub question. It's a sub question in the same thing. Now let's do one more lag compensator question, and after that we'll move towards lead compensator. But this time I would like expect you guys to be doing this same question. G of S is K divided by S into S plus 1 into S plus 5. And the given is KV, that's the compensated KV. It's given as 18.33. The format of the question is same, so that's why I'm not writing the question. Peak
So
overshoot.
slide is not moving, sir.
The slides are not moving. Is it fine now?
No, sir.
Like screen is not visible or what?
The screen is visible, but it is a.
Like, can anybody else check it? Is it coming for others?
Into us, sir.
Okay, let me write.
Yes. Now it is visible.
Okay. So the question remains the same. I've given you another transfer function, open loop transfer function, and I'm saying the compensated system has the velocity error constant as 18.33 and the overshoot as 16.3%, settling time as 8 seconds. Your question number 1 is, find the dominant poles. Your question number 2 is, again, find the K. Question number 3 is, find KV uncompensated. Your question number 4 is, if lag compensator is designed, what is the value of beta? Your question number 5 is, 0 of the compensator is given at minus 0.2. Find PC. Yes, please. If you have any doubt, I can help, but please try this question. These questions are a bit lengthy. That's why I expect every one of you has calculators around.
Sir, damping ratio is same.
Okay,
0.5.
damping ratio is same.
And omega n is 1 here.
Yes, omega n is 1. Then please find the dominant poles.
So it is a minus 0.5 plus minus j, 0.866.
Yes, so let me write the answers. So dominant pole is, so what were you saying? Minus
minus
0.5.
plus minus j 0.866.
Great. Now find this value of K using magnitude condition. So with this value of dominant poles, just put this in the transfer function, then find. So I know that can be complicated. I'm just writing the answers for K. Will be 4.58. Similarly, then KV uncompensated is equal to 0.9165. Similarly, beta is equal to 20 and BC is equal to minus 0.01. So if time permits, I'll solve this question for you, but please try. Like if you have any doubt, then you can ask for this lag compensator. Otherwise, we'll be going with the design of the lead compensator.
So this is same as previous question. No?
Yes, same.
So we will
Only
solve
the
this
values
as a
I've changed.
homework, sir.
Sorry?
We will solve this as a homework, or we can go for another
Yes,
question.
maybe. But yeah, okay. Just try this as a homework because you'll be having assignment. I think this is the assignment, practice assignment problem.
Yes, sir.
So is this clear? Anybody is having any doubt? Then maybe I can clear or we'll move. Okay. So let's move towards the design of lead compensators. As I said, the lag compensators, they are used to improve the steady state characteristics. That's the steady state error. But here, this lead compensator, so it's used to improve the transient response, right? In the transient response, you have overshoot, etc. Now, how to tackle this design process? Like, what is the design procedure? I'll tell you step by step. Like, so basically, you'll be given in the question some transient specifications which you want to meet. Like you want overshoot to be this much, settling time to be this much, etc. So you'll be given with transient specifications. As I gave in the previous question, same you'll be given as transient specifications. Then what you do, the next step is what? You find the desired closed loop poles. That's the dominant poles. Now you know how to find this desired closed loop poles. Then you find the root locus of the uncompensated system, right? And locate this closed loop pole on the root locus. So if this lies on the root locus, so you draw the root locus and then you see whether this desired closed loop pole, whether it lies on root locus or not. So if it lies on root locus, then you don't have to do anything. You just have to adjust the gain. You just have to adjust the gain. What does it mean? I'll tell you. Well, we did this question. We did this question. So we saw this. Um, this sorry. Yeah. So while we solved this question, we saw this this desired closed loop poles was lying on the root locus. Then we know what is root locus. In root locus, we vary the gain from 0 to infinity, and we get the desired characteristics. So our root locus starts here from here. Then as t tends to, as k goes to, as k increases, it goes in this direction, right? This direction and this direction. But we are given our overshoot should be 16.3% and settling time should be 4 seconds. We will traverse through this root locus. We will adjust this gain because while I traverse through this root locus, I am actually adjusting the gain. So I will traverse through this root locus such that these specifications are met. So I'll stop there. So I could see my specifications are met when k is equal to 4. So when I take k equal to 4, I get the desired overshoot, I get the desired settling time. I stop there. So there is no need to design any compensator, etc. So I just do the gain adjustment, I'm done. But what if my root locus do not lie on the root? What if my desired pole does not lie on the root locus? In that case, we have to reshape the root locus. We have to shift it, right? So one way was if my desired closed loop pose lies on the root locus, then you don't have to do anything, just gain adjustment, we are done. But what if my desired pole it does not lie on the root locus? So what you have to do, you have to reshape the root locus such that your desired pole comes on the root locus, because when your desired pole comes on the root locus, then your characteristics, the transient specifications are met, right? So that's what we'll be doing here. So one way of meeting this design criteria is by designing a lead compensator, which is again the same transfer function. I'll write S plus ZC divided by S plus PC. Right? Now, in lag compensator, I told you this ZC and PC, they have to be very close to each other because I do not want to distort the transient specifications. But here I want my transient specifications to be met. So I will distort my transient, my root locus such that my specifications are met. I don't care about the steady state. So here in case of lag compensator, this ZC and PC were placed close to each other, but here they are not placed close to each other. So where they are placed, what will their position be? That depends on the design, that depends on the specifications that we want to meet, right? The difference is the ZC and PC here, in case of a lead compensator, they are not placed close to each other, right? So I hope you got the idea. This will be more clear as we do questions. So let's do this question. Let's assume we are given the same transfer function I take. GS is 4 divided by S into S plus 2. So I took the same transfer function so I'll show you. So I took this transfer function. K was 4. So I took GS K divided 4 divided by S into S plus 2. And with some specifications which were given, we found that our desired pole was coming on the root locus. Now I will change the specification such that my pole does not come on the root locus. Okay, so this is my question. GS divided is equal to 4 divided by S into S plus 2. And my design criteria is I should have an overshoot of 16% and a settling time of 2 seconds. I don't care about the steady state error, right? So first question is, you are given transient specifications. The next question, what you'll do, you'll find the closed loop poles, and then you'll see whether those closed loop poles, they lie on the root locus, then spill gain adjustment. But here I have chosen these specifications such that my closed loop poles do not lie on the root locus. Then we have to reshape the root locus using lead compensator, and accordingly we will get the desired specifications. So now let's proceed to find the desired closed loop poles. We are given overshoot as 16%. It means minus pi zeta under root of 1 minus zeta square. Please solve this. Is equal to 0.16. Okay, if anybody is getting any difficulty in solving for this zeta, let's solve it for this problem step by step. So I will take this e here. It will be minus pi zeta under root of 1 minus zeta square is equal to natural log of 0.16, which will be equal to minus and minus will go. If I put the value of this, it will be 1.83, which you solve. So then you don't have to do anything, just square it. You can directly apply the formula of gamma, but I'm making it like sometimes we do not remember the formula. That's why let's go step by step. So it will be just squaring it, 3.35. And after just multiply, this will be 3.35 minus zeta square into 3.35 pi square zeta square. So it will be zeta square pi square plus 3.35, and zeta will be again, zeta is coming out to be 0.5. So I got zeta is 0.5. Then what is my settling time? My settling time is 2 seconds. It implies 4 over zeta into omega n is equal to 2 seconds, 2 and 2. It implies my zeta n is equal to 4. 4, I'm not bothering about the units. Okay, so my omega n will be 4 radians per second. Then what will be my desired pole? It will be minus zeta omega n plus minus j under root, okay, sorry, j omega n under root of 1 minus zeta square, which is equal to minus 2 plus minus j 2 root 3. Okay. Anybody has any doubt until here? Well, let's draw root locus. My one pole is at here, 0, and my another pole is at 4. Sorry, was it at 4? Yeah, sorry, it's at 2. My another pole is at here, it's at 2. So it's 0 minus 2. What will be my root locus? My centroid is at minus 1. So my root locus will be something like this. So it will go to infinity from here. So this is my root locus. Now let's locate my desired pole. So my root locus, my desired pole is somewhere here, right? And same the complex conjugate pair, right? Because it is minus 2 plus j2 root 3. So is it lying on the root locus? Is it lying on the root locus?
No, no.
It's not lying on the root locus. Just doing the gain adjustment, like we cannot, like we have to do something else. So just doing gain adjustment will not serve the purpose. So so what we have to do, we have to shift this root locus to include this point to ensure that this point is also on the root locus. So what we will do, so how we can say this root locus is not on the root locus? Because then it has to satisfy the angle condition. And we can see if we put this value SD, that is -2 plus J2 root 3, if we put in the original transfer function, and then if we find the angle condition, the angle should be a multiple of 180. So we can see it's not satisfying the angle condition. Therefore, it's not lying on the root locus, which is obviously visible on the root locus as well, that it's not lying on the root locus. Now what we will do, we have to compensate, like we have to, there is some angle deficiency because it's not lying on the root locus. There is some angle deficiency because of which it's not lying on the root locus. So we will provide that angle deficiency such that my angle condition is satisfied. And when my angle condition is satisfied, my this point, this pole, -2 plus J root 3, it will lie on the root locus, right? So in that case, what we will do, we will design a lead compensator, right? So let's first do this. So let's assume I'm just, yeah, this is 90-degree. This is some theta1, right? So let's assume this is theta1, and let's assume this is theta2, right? So when I am adding, when I am designing a lead compensator, then what I am doing? So I am designing a lead compensator. It means I am Kc S plus Zc divided by S plus Pc. So I'm basically adding a zero and a pole
Have you
such
written
that
theta
my,
one? Have you
sorry,
written theta? Have you
yes,
written
yes,
theta
yes.
one under? But it is not visible, sir.
Which, what is not visible?
Theta one, where it is a theta one?
So this angle,
Yes, yes, yes. Now it is visible.
yes. So what I'm saying, so this I am adding this pole and zero such that my angle condition is met. Or in other words, I am providing the required angle deficiency to my system so that my desired pole, it comes on the root locus. So let's assume this angle is theta1, this angle is theta2. And in case of a lead compensator, my zero leads the pole, right? So let's assume my zero is somewhere here and my pole is somewhere here. So I added a zero and a pole. Let me mute. So what I did by adding by designing a lead compensator, I'm adding a pole and a zero. So there will be angle contribution from my zero, that is theta z. There will be angle contribution, that is theta p, right? So we know that theta z gives the positive angle contribution and theta p gives the negative angle contribution. So I can write it like this: theta z minus theta p. Then I have two more poles, which is theta 2 and theta 1 is equal to, it should be equal to 180, right? So in order for that point to lie on the root locus, this angle contribution, it should be 180. Or we can write this theta 1, we can write it like this. So we can write it 180 minus theta. So it is 180 minus theta. So actually this angle which this point is making with this, we have to take it clockwise. So this angle is actually theta 1, right? So this actually is theta 1, and theta 1 can be written as 180 minus theta, and this is theta. This angle is theta, and theta 1 is this angle. So theta 1 is 180 minus theta, right? So let's put in the values, right? So we have theta z minus theta p. What is theta 2? Theta 2 we can straight away see it's 90. So theta 2 is 90 degree minus, what is theta 1? 180 minus theta. And what is theta here? So you can see this theta, we can write tan inverse of this over this. So we know the value of this is 2, and similarly this is also 2. So it's tan inverse of, sorry, this is 2 root 3. So it will be like this. Tan in, I just using basic trigonometry. So it's tan inverse 2 root 3 by 2. Right? So this should be equal to 180 degree. If we simplify this, you will get theta z minus theta p is equal to 30 degree. This is the angle deficiency. This is the angle deficiency. So when I design this lag compensator, I'm actually putting a 0 and a pole to this system, and by using this, that angle and pole, that will provide an additional angle of 30 degrees, such that my angle deficiency is met, so that my point lies on the root locus. So when my point lies on the root locus, then accordingly my root locus will change. So it will, initially it was something, and now it will be something else. Right? So this theta z minus theta p is equal to 30 is the angle deficiency. So the compensator, this has to contribute an angle of 30 degree, so that angle condition is satisfied. I'll write here, the compensator has to contribute an angle of 30 degree, so that angle condition is satisfied. An angle condition is satisfied, it means my pole is lying on the root locus. Now again, I'm saying that this is a design problem. There are n number of ways to design the lead compensator for this problem, right? Because this theta z minus theta p equal to 30, there are n number of ways we can design, we can get this value. For example, let's assume choice number 1, theta z is equal to 60 degree and theta p is equal to 30 degree. In that case, theta z minus theta p is equal to 30 degree. Or another choice, let's assume this theta z is 90 degree and theta p is 60 degree. So again, we will get theta z minus theta p as 30 degree. But which one is better? So we will see that which choice will give us better results. Like if we have some specifications, which choice of this theta z and theta p which will give us good results. So now we know these theta z and theta p, we know these angles. Let's again draw the root locus, or just I'll compute zc and pc. So my one pole was at 0, other pole was at -2, right? There was 1 0 here and 1 pole here. The desired point was here, right? So we got this angle something. This was 90. So we got all these angles now. So this theta z we're assuming to be 60 degree, and theta p we're assuming to be 30 degree. This is 90 and this is also 60 degree. Right? So we now we need to, with these angles, we need to find this location. This is ZC, this is PC. So we need, this is basic trigonometry, I know. And this, what is this? This is 2 minus 2 plus, this is actually 2 root 3, this point. I'll just write 2 root 3, the magnitude directly. So now I need to find this width.
So this
I need to,
angle we have chosen, theta z is equal to 60 and theta p is equal to 30. This is arbitrarily we have chosen.
yes. I told you this is a design problem.
Okay.
So it has, we can design it n number of ways, but I'll show you which design is better.
Okay.
But for your questions, I'll tell you, because you'll have to give exact values. So for that, we'll follow what is done in the NPTEL lectures, and I'll do that one as well. I'll tell you. But this is for learning purpose, how you can design. So we need to find the ZC as well as we need to find this whole length BC, right? So this is also 90 degree. So in this triangle, can we write this? Tan of 60 degree, which is equal to 2 root 3 divided by ZC minus 2. I'm only writing magnitudes. Please do not confuse with the values, because it's in left hand side. Since I'm not dealing with like I'm only concerned with magnitudes here, because I want to find the length. So this will be root 3, 2 root 3 divided by ZC minus 2. Root 3 and root 3 will go. It implies ZC is equal to 4. So this whole length is 4. Now I need to find PC, right? So again, in this triangle, this right triangle, I'll write tan of 30. So for PC, I'll write tan of 30 is equal to 2 root 3 divided by, let's assume this to be x. So it will be 2 root 3 over x. Then it will be equal to root 3 over 3 is equal to 2 root 3 over x. This and this will go. It implies x is 6. So this x is 6. Then what is PC? 6 plus 2. PC is 8. So my PC will be, it implies my PC will be 8. This is basic trigonometry I'm using. My PC is 8.
Sir, I cannot see what we are writing. So, yes. Slides are not visible.
Okay, is it now visible?
Yes.
So now with this choice 1, let me write GC1. That will be KC into S plus 4 divided by S plus 8. Right? So my compensator number 1, which I have designed by taking theta P, theta Z as 60 degree and theta P as 30 degree, has come out to be this. KC is S plus 4 divided by S plus 8. And how do you find the value of this KC? Again, this compensator, it will be connected like this. GC1 G. So it's connected like this. So in order for us to find the value of this KC, what we will do is go for the magnitude condition, that is GC of S. Add the dominant poles, because now, sorry, desired pole, because now I have reshaped my root locus such that my point, which is now lying on the root locus. So I'll satisfy this magnitude condition, and by solving, I'll find KC as 6. You'll do this. This time is not permitting, which implies my GC1 is equal to 6 into S plus 4 divided by S plus 8. This is the required complete compensator for this system such that our desired transient specifications are met. Now let's go for choice 2. What was choice 2? Choice 2 was theta z is equal to 90 degree and theta p is equal to 60 degree, right? So it means we have one pole at 0, other pole at 2, and we have to add this theta z and theta p such that these angles are satisfied. So we have this desired pole here. So if theta z is 90, it means this pole will be here, placed here, right? And this theta p is 90, means this pole will be here, 0 will be here. This is 60 degree and this is 90 degree, right? So I know now this z, it's very easy now. I already know this is -2. So it means my zc is 2. Similarly, I had solved this pc equal to 60. So when I solve this pc equal to 60, it means now my zc becomes pc. This might be confusing at the first instant, but when you when you like see it again and revise it, it will be easier. So my PC will be 4. You just do the basic calculation if you don't want to see it like this. And what will be my GC2? GC2 will be KC into S plus 2 divided by S plus 4, right? And again, when you satisfy the magnitude condition, you will find KC is equal to 4. It implies my GC2 is equal to 4 into S plus 2 divided by S plus 4. So I have designed two compensators. For this system. Now I'll show you the difference. So we were given this G of S is equal to 4 divided by S into S plus 2. Now we made two compensators for the same. One was 6 into S plus 4 divided by S plus 8. And GC2 was 4 into S plus 2 divided by S plus 4. Correct? So now let's do the root. We already know the root locus of our initial transfer function G of S. Let's again do it for the completeness. I'll just draw it arbitrarily this time. So one pole is at 0, other pole is at -2, and my desired pole is somewhere here, but my root locus is this, right? And this was my desired pole. Now, when I use GC1, what happens when I use GC1? So when I use GC1, it means I'm adding. So let's draw the root locus again. So it will be somewhere like this. We have pole here, and we have a pole at -2. We have a 0 at -4. We have a pole. We have a pole at -8. Now, which part? What? Like, see, this is the part of root locus. This region is a part of root locus. Similarly, this region is a part of root locus. So root locus will start here and terminate at this 4, 0, like at this 0, which is 4. Then there will be some breakaway point. This breakaway point is here, and my desired pole is here. So what will happen? My root locus will be now something like this. So when I added a lead compensator, my root locus shifted. I reshaped the root locus, so I got something like this, right? But if you see, uh, I am adding this compensator, which is a lead compensator, and I am adding a pole to the system. If you see, okay, of course I'm adding a zero, but at the same time, initially my system was second order, but as I will include this compensator with this system, it will be s into s plus 2, and I will add another pole. Now my system will become as third order. Now my system will become as third order, and whatever calculations, be it rise time or overshoot or settling time, they are only valid for second order. So even though I'm able to meet the specifications, if you do this thing in MATLAB, you will see you will not be exactly obtaining an overshoot of this much. What was the overshoot specification? So you needed an overshoot to be in the question, and you needed overshoot to be 16%. But with this compensator, which is giving me a third order system, you will not be able to achieve 16%, right? So there will be a mismatch. Why? Because whatever these formulas you have used, they're valid for second order system, but here my system is becoming third order, so there will be slightly mismatch. So now in the second case is, which is GC2. So with GC2, what happens to the root locus? Just I'm making the root locus here. I have one pole at origin, other pole at -2, and my desired pole is at here, another one is at here. Then what I did, I added a zero here, and I added a pole somewhere here. What was my pole location? My pole location was, yeah, 4, -4. Now this, if you see here, this zero will be cancelled with this pole. So there will be pole zero cancellation. So when there will be pole zero cancellation, this point will not be there. They will be cancelled. So when this pole at -2 and 0 at -2 will be cancelled, what will my root locus look like? My root locus will look like this whole region. Then if you find the centroid, it will be something like this. So your root locus will be something like this. Already your desired poles are coming on the root locus. But there is one important thing here. The one pole has been cancelled. So one pole has been cancelled, where again this second order system is preserved. The whatever calculations we have done there, they stand valid. We will be achieving a closer like specific, the specifications at this with this compensator will be accurate. So again, try this with MATLAB. So you have a open loop transfer function, you have a compensator 1 and compensator 2. Just join them in like feedback, then see the step response, right? So you will see the step response, and then again with this desired pole, the overshoot should be 16% and settling time should be something. So you can see that is being this GC2, the lead compensator, which is for which there is a pole zero cancellation. So that is more accurate. The calculations for that is more accurate. So that's what I said. These are design problems. They have n solutions, right? So this was for learning purpose. But if you have assignment problems where you don't have you have like uh, uh, multiple choice questions, so there you will have to fit in some. You will have to select some answer. So in that case, there is a formula which you will use. So let's do this question. G of s is equal to 1 divided by s into s plus 1. It's given that gamma is 0.6. Settling time is 4 seconds, right? So settling time is 4 seconds, and you have to first find what is the magnitude of angle deficiency, you'll first find. So in this question, you have to find the open loop transfer function is given as this. It's desired to design a lead compensator such that the closed loop system has a damping ratio of this and a settling time of this. So when I say damping ratio of this, I get some overshoot as well. So then you're asked to find the magnitude of angle deficiency. It means the point will not lie on the root locus. The pole will the dominant pole or the desired pole will not lie on the root locus. And in order for that to lie on root locus, you'll design a lead compensator. And when that lead compensator is done, then you have to find, okay, how much angle that compensator needs to supply so that this point comes on the root locus. So that remains the same. So you have to follow these steps. Whatever I did until here. So you add a zero, add a pole here. So add a zero, add a pole, then do some calculations. You'll get angle deficiency. So until angle deficiency, you have to follow my procedure, whatever I told. So for this question, my dominant pole SD or desired pole will come as -1 plus minus J 1.33. Again, it will not come on the root locus, then you'll find the angle deficiency, and my angle deficiency, theta Z minus theta P, just follow the same procedure, and it's sometimes called as phi. And it's coming out to be 36 degree for this question. So when you are done with this angle deficiency, then what you do, I'm giving you a shortcut. So you are done with angle deficiency, then you find something called gamma, which is equal to half of 180 degree minus theta minus phi. So what is this theta? Where this theta is cos inverse of gamma. So you know theta because you know gamma, you know phi, phi is angle deficiency, so you know gamma. So in this case, gamma is coming out to be 45 degree, right? Then, so what you need to find? So what you need to find ZC and you need to find PC. Right? And what will be ZC? ZC's formula is omega n sine of gamma divided by sine of gamma plus theta. Right? Which if you solve will be 1.67 into 0.707 divided by 0.9899, which is coming out to be 1.1905. Just simple calculations. Everything is known. Similarly, you will find PC. PC will be omega n sine of gamma plus phi divided by sine of gamma plus theta plus phi, which when you solve, you will get 2.33. So with this, you got these values. You got these values. Yeah, this ZC and PC. So you got these values. No need to find those angles or whatever I told you. So you got these angles. So you know the compensator. So what will be the compensator? GC of K, GC of S. That will be KC into S plus 1.1905 divided by S into, sorry, it will be S plus 2.333. Right? So in order for you to find the value of Kc, again, the magnitude condition should be satisfied. This should be equal to 1 at S equal to SD. Then you will find the value of Kc to be equal to 3.1107. So finally, your compensator will be 3.1107 into S plus 1.1905 divided by S plus 2.333. This is the required lead compensator that meets the desired specifications. So this is for your assignment problem, but in general, if you want to design, so again, there are n answers. So this is from your slides, this design. What you have to do, just find the angle deficiency, right? So there is one other way for angle deficiency. No need to write this theta z and theta p. You can directly consider this as angle of G of C S, because this is the angle which this compensator is applying. More specifically, what you have to do. So if you have GC, then you have G. So this is the system you'll be having when you connect this GC with this system G. So what you have to do, this whole GC into G, the whole contribution of angle should be 180 degree. So you know the value of G because everything is given. You can find the angle of G. So angle contribution of GC plus angle contribution of G should be equal to 180. Then angle contribution of GC should be equal to 180 minus angle of G. So this is the angle deficiency. This is one other way, but that one is more better because there you realize that, okay, theta Z is the angle from poles and theta P is the angle contribution from the poles. Sorry, Z was from the zeros, and that way zero always gives a positive angle, pole always gives a negative angle, and then you're more able to focus. Is it clear? Anybody has any doubt?
It is clear, sir.
Yeah, I think now you should be able to solve those assignment problems. I try to be as simple as possible. Otherwise, these problems are very complicated in general. So that's it. If anybody has any doubt, please ask. Otherwise, we'll just end this session.
There is a one alpha beta
Yes.
is equal to 1 is given.
Alpha beta. What is alpha beta?
It is a gain in case of the lag compensator, and alpha is the gain in lead compensator.
Okay.
When
Okay, means
you
Kc
design
and
the lead
Kg.
lag
Okay, lead lag. Sorry. Yes.
so lead lag, both the compensator is we use, then alpha beta is equal to 1. Assuming alpha beta is equal to 1,
Okay.
we have asked the velocity error constant.
So what is the question?
Question is something different.